Thank you to both of you for the invitation. It's my first summer in Les Houches, and given that it's 40 degrees in Paris today, I'm very pleased to be here. In fact, 41, 42. And so today I'm not going to talk about neural networks. Okay, so I understand this has been a topic of many of the talks, but today I will talk about something which is totally different. And so why should you care? I think we should care because there is lots of problems in like machine learning and optimization where we claim to do large-scale inference, but of course size is relative to what you're trying to achieve. So if you do convex optimization, then large could mean like billions, trillions of parameters. Okay, so very, very large. And this corresponds to the classical logistic regression, for example. So I'm not going to talk about that. That could be the topic for maybe like 10 years ago. Then you can do like still large-scale optimization, but with some structure. So it's non-convex, but you have some structure. And I think like all the neural net are an example of that. So it's non-convex, but you can still say things which are relevant, and probably a lot of talk about that. But today I want to focus on situations where the curse of dimensionality kicks in. So when D will be large, it will not be like millions, it will be like tens or hundreds. Okay, so the motivating example is global optimization. When you want to optimize a function, my motivation for today at least, you want to minimize over x in x some function h. And you can think of capital X as being minus 1, 1 to the d, the interval by the cube, or just the vertices if you want to do a combinatorial optimization. And d will not be so large, and of course h will not be convex. Okay, so this is our goal of today, and the goal is to find some x hat, okay, in x such that h of x hat minus the minimal value is less than epsilon. Okay, it's a classical like criterion for optimization in functional values. And of course, h of x hat is bigger than this. Okay, so and the goal is to give some x hat. And what I mean by global optimization is that I just don't want to just regular descent and hope for the best. The goal is I want an x hat for which I can give you the epsilon. Okay, and the epsilon I can give you either a posteriori. I run my method and I get an epsilon, and I can certify that I optimize my function up to epsilon for sure. It's like a formal certificate. But I also want to have some a priori bounds on epsilon. Okay, I have some budget of computations, and I want to know how small can I make epsilon before I even see my functions. So of course, it is very generic, and you need to have ways of accessing h. So you will need some oracles on h. So I will build various oracles, but you can think of the classical oracle first order. So h of xi for some xi in x. Okay, and what we see tomorrow, we'll see also some Fourier transforms or Fourier series of h. Okay, so you need to access h in some ways. Okay, and that will be explicit when we go along. Okay, I've mentioned the motivating sets. Okay, so there is minus 1 to the d, minus 1, 1 to the d. Okay. And this will be mostly for today. But one of the goals of this like set of lectures is try to go a bit beyond. And what the tool I will use. Am I forgetting something? No, the tool I will use is the so-called sum of squares. Okay, and the goal will be for today to explain what sum of squares are. Okay, and to give you the classical notions. And the goal of the set of lectures is to go beyond optimization. I just don't only want to solve those problems, okay? But we'll see that the tool that you need to solve that can be reused for optimal control, reinforcement learning, optimal transport, many problems where you have where the curse of dimensionality may kick in. And the goal will be to go beyond sum of squares of polynomials. Okay, so you may have heard classical setup would be to consider h being a polynomial and using like a sum of squares of polynomials. The goal is to go beyond those two aspects. Okay, but today I'm going to mostly focus on optimization as a motivating example. So don't hesitate to interrupt me if you have questions. Okay, so this is I prefer when it is interactive, and if you have comments as well. So there are experts in the room on sum of squares. Okay, so if he or she has a comment to complement what I'm saying or to object, feel free to do so. I think it's meant to be interactive. All right, any questions before I start? Okay, so let's start by first showing that all problems are convex. Okay, so this is important, and this is what I learned from Laurent Algaoui in Berkeley. I took his class. So all problems are convex. Why? Because if you take x, okay, 0, 1, you take your function f, okay, f of x, and minimizing f is equivalent to finding the largest lower bound. Okay, so we call that C. So you can see the mean. Okay, so here in this talk, mean, inf, is all the same. Okay, so you're in physics, no? So you shouldn't care so much. Okay. Sorry for I shouldn't say that. I will not say it again. Okay, so.
Can I ask a question, actually?
Sure, go ahead.
So, you said that minimizing f is equivalent to finding a lower bound.
Yeah.
But if I tell you the lower bound, you don't necessarily know where it's achieved.
That's a very good point. That's a very good point. So clearly, what you would like is find the tightest lower bound, and then find where it is achieved, and I'll come back to that after. But that's a key point. You can either want to find the minimal value, or find a minimizer. Those are different things. I was planning to more or less avoid talking about it, but I can mention it because this is important both in practice and in theory. So how can I formulate this as a convex problem? So you sup over C for C in R, such that for all x in X, h of x minus C is positive. Okay, so I have one variable C living in a convex set. I have a bunch of inequality constraints in C, all convex. This is convex, so I have a convex problem. So all problems are convex. Okay, so that's very generic. So of course the catch is that here you have a potentially infinite set of inequalities, and very infinite, not even countable. Okay, so it's often a dense set of inequalities, but still this is the starting point. Okay, and so why is it interesting to look at that? Is because we're going to say that equivalently h minus c is a non-negative function. Okay, so it's a very trivial reformulation. And so the idea is that if you want to do optimization, it's equivalent. Okay, one way of doing it is to be able to deal with a set of non-negative functions on X. Okay, so and so the goal will be how can I find models on the set of non-negative functions which are easy to manipulate? When I say easy to manipulate, typically in a linear way. I want to preserve convexity, so I need a set of models which is linear, easy to access, and tractable. Okay, so this will be the goal of today. And there is a dual view, because when you have a convex problem, there is always a dual problem. Okay, so let's look at what would be the dual problem. This is very also learned from Laurent Algaoui. So we have a set of inequalities. Okay, so I'm going to add a Lagrange multiplier for each of those. And the Lagrange multiplier here, I will call it mu of x. And it will be positive, okay, because I have an inequality. And here I'm going to use like integrals and sums in a non-rigorous way. This can be made rigorous by looking at measures and not like functions, but let me avoid this now. So I can write this as the inf over x in x of the sup over the Lagrange multiplier, which is a function from x to r plus. I have my c. And then I add, so the Lagrange multipliers times the constraints. And so here, I'm supremum, I have positive. So trust me, this is the integral of mu of x, h of x minus c. Okay, dx over x. Okay, so this is the Lagrangian formulation. I will invert the sup and the max. Okay, and I get the sup over mu from x to r plus. And now what I obtain is that when I am, there's not x, it's, oh la la la, it's sup over c and inf over mu. Sorry. Okay, so that's okay, so the problem is the supremum over c. I have c, supremum over c, I keep the objective value, there's the infimum over the Lagrange multiplier. I invert the inf and the sup because it's convex. And now what I obtain the integral of mu h, integral of mu of x, h of x dx. And when I optimize over c, so I optimize the linear function. So this will create a constraint on mu. And I get 1 equal to the integral of mu x. So I get such that integral of mu of x dx is 1. So now what I have done, the dual problem is very simple. I want to optimize over all mu's which are essentially positive and sum to 1. So I optimize over all measures essentially, and I optimize over all probability measures the expectation of h. Okay, so if I put my 1D plot, this is my h. Okay, so the optimal mu will put all of its mass around a Dirac, would be a Dirac around x star. Okay, so this is just the dual problem, which is also very natural. Optimization is like finding the minimal expectation of h over a given measure. Okay, so this is like somehow trivial, but this is like the starting point. And why is it important? Because you have a dual view between modeling non-negative functions and modeling distributions. Okay, and this will come up as well in the sum of squares. You can see it through the function view, sum of square view, or through the moments. Okay, so depending on the authors, you go one way or the other, and it's often quite confusing. Okay. Any questions so far? No? And to go back to your question, so this is the mu will allow you to get back the minimizer. Okay, so from the mu, by doing some more operations, you can find the, you want to approximate the optimal mu, or you approximate optimal mu by a Dirac, and there are ways of doing it. All right, so let's done that. All right, so now let's go as sum of squares. Because the ID is very basic, so I will say SOS for sum of squares, okay? And tomorrow I will talk about kernel sum of squares. That will be KSOS, in French, Cassos. All right. So can you explain to your friends what it means? Okay. And all right. So now, okay. Now the question is, so I have to create some. Yep. So the overall ID in the sum of squares is going to model functions. So G from X to R as a quadratic form. So G of X will be a quadratic form in some feature vector phi. Yeah. So G times phi of X, where I'm going to get phi of X. So phi goes from X to some So I put complex numbers because I'm going to need like complex exponentials, but you can put RD, okay? So this is just a conjugate transpose. It's just a quadratic form, and G here will be a Hermitian matrix. Okay, so G star is equal to G, so that this is always real valued. Okay, so the idea is to model things like that. So examples, polynomials. Okay, if I take phi of x like in 1D, phi of x is 1x, x squared up to x to the r. I get, at the end, I can model all the order 2r polynomials in 1D. If I add more dimensions and more monomials, I can model all the polynomials, all the multivariate polynomials. Later, I will show as well trigonometric polynomials. Okay, so that will be phi of x will be equal to 1 exponential I pi x, exponential minus I pi x, and you add frequencies like 2I pi x, minus 2I pi x, and so on. Okay, so this will be for trigonometric polynomials. Okay, and as you can see here, modeling G, like small g, as a quadratic form is not a strong assumption. You can always design a good phi of x so that you get a nice representation. First thing, very important, capital G is not unique. Okay, for any given small g, there are potential multiple uppercase g. Okay, because you can, if you take phi of x times phi of x, so this is important, phi of x times phi of x, I transpose here, you get 1 x squared, ij is x power I plus j. Okay, so at the end, it's called a Henkel matrix. So that those matrices of that form are called Henkel matrices. And you see that immediately the representation of a function as a quadratic form is not unique. Okay, because your phi of x, they have naturally there is a vector space which is not full that contains all the phi of x times phi of x star. In fact, I will give it a name. We call V the span of phi of x star. Okay, for all x. Okay, so for polynomials, this is just a set of matrices whose value depends only on I plus j. So they are constant across the anti-diagonals. For trigonometric polynomials, you get the Topic matrices. Okay, so for every phi of x, you get a natural like a set of equalities. Right. What I will assume as well, to make my life easier,
can I ask, so the assumption that the matrix is Hermitian doesn't restrict you if the variables are commuting or something like that, if x's commute past each other, is that right?
There is no straight on x whatsoever here. Capital X can be anything. Phi of x is an element of to C to D. So you get like a vector, transpose of a vector times G. So I don't understand the question about commutative.
So the question is, how much of a restriction is it that G is Hermitian?
If you want G to be always real valued, you better be, and phi of x can be complex, like here. It's a sufficient condition, and it's essentially necessary, I would say. But to me, it's not a limitation. But maybe there are examples for which it is not the case. But yeah. All right. So other assumption which I will always use, is that there exists a U. So in C D times D. So all of my matrices will always be Hermitian. Okay, unless otherwise stated. When I say U is C D times D, you should think of C as being a Hermitian as well. Should that phi of x, U phi of x is 1. for all x. So there is the constant function is inside my model class. Okay, so it's true because phi of x already has something like that. And I'm going to assume there is such a u. That u is typically not unique, okay, because if you add to u any element of the orthogonal of v, you get also you don't change the value of phi of x transpose u phi of x, so you also get another u. So there are many u's for which this is true. I'm going to take one, and hopefully all the things I'm going to say will be independent of the choice of u. All right. So now this is the thing, and also SOS. Okay. What would be the key obvious observation is that if G is PSD, okay, so the G positive semi-definite, okay, and since G is assumed to be Hermitian, it has like real eigenvalues, and this is simply saying that all of these eigenvalues are non-negative. And if G is PSD, and this is, then G is non-negative. Okay, so this is the very simple statement. Since G is a quadratic form in phi of x, okay, so if the quadratic form is non-negative, the whole of G is also non-negative. Okay, so this is really the trivial statement. And why is it called sum of squares? Because if G as a sum from I equals 1 to d of lambda I ui star. This is the eigenvalue decomposition where lambda I is a real number which is non-negative because I've assumed PSD, and ui are vectors which are orthogonal to each other. Then you can write G of x as a sum from I from 1 to d of lambda I 1/2 times ui transpose phi of x square. Okay, so if you just take G of x, phi of x, by G of x like this, you obtain something and you get a sum of squares. This is a square function, so you get a sum of squares, hence the name. Okay. All right. So there are two questions which are very natural. Is this an equivalence? If I'm a sum of square, I am non-negative. Is it true in the other direction? The answer will be in general no, but yes in some cases. Okay, so this will be the topic of mostly of today. Other thing, if I need to check, how do I check that? If I give you some G here, how do I check that it is a sum of squares? So this can be checked easily. So the idea is to use models which are trustable. Okay? So you want to make sure that if I'm going to replace non-negativity by being a sum of squares, I want being a sum of squares being simple to manipulate. And so small property, so G of x, a quadratic form, G phi of x, is a sum of square, is equivalent to essentially one of the representations of G like this is a PSD. So there exists some H in the orthogonal of V such that G minus H is PSD. Okay, so this means that so why is it true? Because if I write G of x is phi of x star G prime phi of x. Okay, so I'm a sum of squares if there exists a G prime, so that this is true, and G prime is PSD. Then I need that G and G prime are defining the same function, and they define the same function if apply to phi of x transpose, you get always the same value. So this means essentially that the difference between G and G prime has to be in the orthogonal of all the phi of x transpose. Okay, so this is a simple. There needs to be one element in the orthogonal, so that this is a PSD. Okay? And here, if you know that guy, so if this is simple, and typically it's a finite vector space, so it's simple. So I've mentioned this is V is the set of top-H matrices for the Fourier series. This is Henkel matrices for polynomials. Then you can check, if I give you a function, I can check if it is a sum of squares, but just like a finite dimensional convex feasibility problem, an SDP here, semi-definite program. Okay, so this is the key here is that I will model non-negative functions as sum of squares, and I can handle that set in a computationally efficient way. Okay? So this is the key aspect. G prime. So if so, to prove this, I'm going to assume that G is the sum of squares. So there is a G prime such that G prime is PSD and G of x is something like that.
You want to say that the definition of G being sum of squares is that there exists G prime such that this has this thing, and then
yeah, so
the property is that if you are given capital G, which might not be this G prime, then you can find this G prime by solving the SDP of looking for this H.
Yeah. So the rewriting of this is I have a G prime equivalent to G in terms of functions because I'm only concerned by when I take a quadratic form. I only care about what's happening once I apply it to phi of x times phi of x. Okay, and hence two G's are equivalent if they define the same function. Okay, and being a sum of squares is there exists a G prime equivalent to G such that I'm PSD. And G being equivalent to G prime is like G minus G prime is the orthogonal of V. Okay, so it's a bit abstract, but this is what you need to have, okay, and to make things correct. Okay, I will give example in a moment that will be easier.
Can I ask, when you're given one of these little g's,
Yeah.
assume that you're also given a capital G or a capital G?
A good question. So let's take polynomials. Let's take phi of x being polynomials, okay? So like 1x, x2. Then you're being given a polynomial with 2r degree 2r. You can build a G. There are many ways. You just take the first line, whatever you want. Then you make it Hermitian, okay? To make it Hermitian, so by just symmetrizing it. And then typically, even if the polynomial is the sum of squares, G will not be PSD. So you have to transform G to make it PSD. Okay? So this is a bit the subtlety. All right, so now let's look at optimization. So we look at optimization. So remember that this was the supremum over C such that H minus C was positive. Okay, so this was my reformulation. And now I'm going to replace H minus C non-negative by H minus C being a sum of squares. Should it be bigger or lower than, so sup over C, question, sup over C of C such that for all x in X, H of x minus C is a sum of squares, so phi of x transpose A phi of x, where A being PSD. All right, so you want to, no, but you're not allowed to answer on that. So, what? Oh, just for, okay, so here I have the negative functions, which is a bigger set than the set of SOS polynomials. So if I take the supremum over a bigger set, it's bigger than the supremum over a smaller set. Right. Right, so now this is like a natural relaxation, and this will be the simple Sos relaxation. Okay. Right. So this one you may write it this one if you prefer as if H is represented by capital H, C is represented by C times U. U is my operator that makes constants, is equal to A, okay, plus an element of V complement, okay, because this is only equal for all elements of X. And what I get here, I get a supremum over C real number, A d by d PSD matrix, equality constraints, okay, then it's SDP, semi-infinite program. So this I can run on a computer, okay. So here, from scratch, okay, I have a lower bound on my problem, okay. And the key question is this tight or not? Okay. So the goal of the whole set of lectures is to explore that tightness. Any questions here? No? All right. And so here I have a convex problem. So I'm going to take the dual again, okay, to see, and we will see the moment matrices appearing, and this will be the dual view that you can have. So let's take the dual again. So it's a sup over C. So infimum over mu. So now I'm going to take a Lagrange multiplier for that guy, but this one now is an equality constraint. So the Lagrange multiplier will be a function from X to R. There will not be any more R plus. Okay, there is no need to have R plus like I had before. Before, I had H minus C was positive, so I needed to have mu, which was a non-negative function. So I have the same thing. So I have inf over C plus the integral of mu of X H of X minus C minus.
Maybe it's good to give names just to the dimension of phi. So right, so H is you represent each function little h by capital H, which is m by m or whatever.
Yes. So so here what I've done implicitly, and thanks Boaz for making it like formal. G's are functions defined on X, and G's are quadratic forms. Okay, and I'm trying to use the same letter and uppercase C to say that I'm representing G by capital G. The issue is that the capital G is not unique. Okay, so there are many. So it should be an equivalence class of G's. Okay, but let's keep it like this.
But you're assuming here that you actually
So for polynomials, Fourier say that's obvious. Tomorrow when I go to like kernels, that won't be obvious. Okay, but if I give you a polynomial, you know it. Okay, so this is a case where you access the function by the coefficients.
Okay, the form of the representation. In some sense, you have to specify a form because you cannot represent a general function.
Yeah. So here one phi of x. So here one phi of x. Yeah. So of course, if G is not a polynomial, it won't work. Okay. So here I'm assuming that I am living in the span of phi of x transpose. Okay. But tomorrow it won't be obvious. It will still be true, but it won't be obvious. All right. So if you take the dual, okay, again. Then I can swap E.
Why it is not R plus for mu?
Because I have a Lagrange multiplier for all of those inequalities. There are equalities. Okay, so this is the. Yeah. And now for I swap, so I sup over C and A. Now there is A. Now there is sup over A. Here, PSD. The sup over C will give me the exact same constraint, so such that, so I keep the integral of mu x h of x dx, okay, such that, and I will get the same integral of mu x dx is 1. And now I'm going to look at the constraint implied by A. So if I take this thing, I get the trace of A times integral of mu of x, phi of x star dx. Okay, so when I'm maximizing over A, like in all semi-definite program, when I sup over A, this has a constraint on the linear form that this has to be PSD. Why? Because if this is not PSD, the sup, there's a minus sign. Okay, so if I take the sup over A, if this is PSD, this is always positive. Okay, so the sup of the minus will always be 0. And as soon as I have a non-negative eigenvalue, a negative eigenvalue for this, I can put A along that eigenvector and drive this to infinity. Okay, so this gives me the constraint that integral of mu of x, phi of x transpose is equal to 1. So what I have here now, if you remember the dual problem from before I had the optimal of the infimal of the integral of mu h for mu probability measure. Now this is replaced by mu is just a sign measure, can be any sign, but I replace positivity of mu pointwise by positivity as a matrix of the second order moment of phi. Okay?
Why 1? I didn't understand. Not any.
Oh la la, boy, because I'm stupid. Because I'm 0. No, sorry, I was. Yeah, so here again, so whenever you do like duality, like in a linear program, if A is positive pointwise, this creates an inequality for the dual. It is the same thing for matrices, and you obtain that matrix has to be PSD. Okay, so this is an Hermitian matrix because phi transpose is Hermitian. Okay, it may, if mu is positive pointwise, it's always PSD. Okay, but it's possible that for this to be PSD without mu being positive pointwise. Okay, so this is why you have a relaxation, is that you remove R plus, but you add the positivity of the moment matrix. Okay.
And I guess another way to say that is that you are increasing the set of expectations now to include also numbers that are negative as long as the expectation of any function which is SOS is still non-negative.
Yeah, that's the same thing. Yeah. So why take the dual view? So now you have two views. Okay, when you talk with SOS and you want to look at the tightness, so is it possible to be non-negative without being SOS? Question 1, seen from the SOS view. Or is it possible for mu to satisfy this, okay, and not being positive? Okay, so this is the exact two dual views. So when you look at papers on SOS, sometimes they go through this, sometimes they go through that, and I like both because it's convex duality, so I'll do both. Okay. All right. So one last piece of formality. So for the I'm going to need it tomorrow on Friday. So.
Can I ask actually? Like,
Yeah.
So suppose that h is greater or equal to 0, just so that it has a
Yeah.
sign.
Yeah.
Then you're like incentivized to make mu as negative as you can, right? Like.
Yeah, but you have the summing to one
I know,
constraint.
but you know, if you're given a choice, you would like
Yeah.
to have some places maybe where it's negative.
So that's what you want. You want to put mass where it's negative.
Yeah, right.
But you still want to make sure that you're not violating this. Okay. So if you remove this, the infimum is minus infinity. Okay. Here you can always drive one value to minus infinity and having the others like compensating to get like the integral being equal to 1. But this compensation is not possible if you have this constraint. All right. So the other, like last last proposition. So this is so if h of x is phi of x transpose h phi of x. Okay, so if you assume that h happens to be a polynomial, if phi of x is a polynomial, for example, then you can rewrite this as the trace of h times the integral of phi of x transpose. Okay, and same thing here. You can rewrite this as the integral of the trace of u times the integral of phi of x transpose. Okay, equal to 1. So you can rewrite all of the problem through that moment matrix. Okay, so essentially, when you deal with the moment view, you can just look at moment matrices, and we're going to call the proposition that's inf over x. So this is a trivial statement. Okay. Yeah.
The integration is with respect to mu x, right?
To mu x, yes, mu x. Sorry. Yeah. Mu x. So trivial statement, the inf. So this is a linear form. So this is equivalent to this is the inf of x in x of the trace of h times phi of x transpose. So this is just a trace trick. Okay, and this is equal to the inf over sigma in k. And I will define k of trace of hk, for k being the convex hull of all phi of x transpose. Yeah. Convex hull. So convex hull of phi of x transpose. And if I want to be super formal, it takes the closure of the convex hull. So this is a trivial statement, which is always true. Whenever you take the infimum of a function which is linear in one of the parameters, okay, you can always replace what is on the right side of the linear part by its convex hull. Okay, so it's always true. Okay, so this is just a statement that when I have a convex set, when I maximize over the direction h, okay, so this will be one extra point of phi of x. Okay, I always, when I maximize linear function of a convex hull, I always end up in an extreme point. Okay, so when we deal with like combinatorial optimization later today, then this will be the image. I have the set of phi of x transpose when x is discrete, will be a set of points. Okay, you have a convex hull, and this will be the this is inequality. Okay, there is no relaxation here. Okay, you can always replace the minimization of a linear form by the linear form times an element of the sigma here. Yeah, sigma. Okay. So this is always true. So why is there relaxation? Because I'm going to find outer approximation of that set K. Okay, this is often the way you derive convex relaxations. Okay, so if you, in most papers dealing with convex relaxations, they start by their problem, they squeeze it in a form where you see some convex hull appearing, okay, and they relax the convex hull in some way. Okay, and so here, the way we relax the convex hull is, so this is, and then we go to what only examples, and then we'll be done.
Sorry.
Yeah.
Can you remind me what's the convex hull of the matrix?
Oh, okay. So the convex hull, okay, is a set of sum of I alpha I of phi of xi, phi of xi transpose is all the convex combinations, okay? So sum of set of alpha I, where alpha I is a positive family, so that sum of alpha I is 1, and xi is in X. Just a set of convex combinations. Okay, so convex hull. So, for example, here, if those are my points, then all convex combinations are any element of the hull. Okay, and so here, capital I is finite. Okay, so a set of finite, convex combinations. That's why you need a closure if you want to be like very, very formal. Right? And so what is SOS? So SOS relaxation is what? Is equivalent to saying that K is inside K hat, which is a set of sigma, which are PSD. Okay, trace of sigma U is 1, and sigma is in V. Okay. So remember, V is a span of Furbeck's transpose. So if you are in the convex hull, you are in the linear span. Okay. So if you are in K, this is true. Okay. If you are in K, this is PSD, this is positive, so sigma is PSD. If you are in those sets, because U gives you 1 for all of those dot products, the alpha sum to 1, then you get trace of sigma U being equal to 1. So it's trivial that, direct that K is inside K hat. Okay? And typically when you derive relaxations in a particular example, you often do this. Okay? And when I will do max cut in a moment, I will do exactly that. Okay? This is much more natural when given an example. But in generality, you have, if you want to have, so this is a moment view. Okay, so this is, you rely only on sigma. But when you see this, it's not obvious where the term SOS comes from. Okay? So this is why it's, you need this dual view. Either you see it through moment matrices, where it's somewhat direct, or you see it through sum of squares. Right. Now I'll go over examples and we'll be done for today.
If sigma is in V, isn't it automatically positive semi-definite?
No, because V is a linear span. So V is a set of combinations where alphas are just real numbers. Okay? All right, so let's go through examples.
Is that the only sort of generalization to think about? Like, I think about K as that, and then I think about K hat just as the alpha of any sign, but still such that sigma is positive.
So what is the question exactly?
To think about K
Yeah.
hat.
K hat is just an outer approximation. So you know that if you're in K, you have to be in K hat from basic principles. Okay, and it turns out that sum of squares is exactly this. Okay, the problem will be that it will typically be strictly superior. Okay, you have the image like you have K. This is K, and what we have is that K hat will be a bit bigger. Okay, and since you're a bit bigger, you won't have equivalence. Okay, you will always get the bound. But if you want the exact optimum, and I want to get a certificate, I will need ways of cutting pieces to get closer to K. Okay.
What I'm trying to understand is what I'm adding to K hat.
I'm subtracting. Okay, so whenever you're in K hat. Okay.
Yeah. What's in K hat which is not in K?
But we'll see.
Okay.
Okay, we'll see now. Okay.
But you can write it, think of sum of alpha I when alpha i's don't have to be, it's the same, like think of the alpha as mu I. They don't have to be positive, but they have to still...
Yeah. But I'll give examples where we have K and K. Examples. Okay. Okay. So let's start slow.
This 2 is the U from assumption 2, right?
Excuse me?
U
Yeah.
is the U from assumption 2.
U is the assumption that phi of x times u times phi of x is always equal to 1.
Okay.
So example, first take x being discrete. Okay, let's take a set with d element. Okay, so phi of x, okay, goes from x to Rd for simplicity. Okay, and so here, so this means that you have, okay. So the question is, so the goal is to check, to have conditions under which I have tightness. Okay, so there are will be two views. So there'll be two views, I remember, two views. So non-negativity equivalent to SOS, or k equal to k hat. Okay, so there are two what?
The DRC.
No, yes, no. Let's put it n. Okay. So what should come out from like just what we have seen before? So we have two questions which are equivalent. Are all negative functions SOS? We know that this direction is correct. Okay. And is k equal to k hat? We know that k is inside k hat. Okay. And those two, when one is equal to the other one is equivalent to the other. Okay. There is like two views to the same thing. All right, so let's be simple. Let's take the so-called like one hot encoding. Okay, so let's say you map. So phi of x, phi of 1 goes to E1. Okay, phi of 2 goes to E2. Okay, and you take d being equal to n. Okay, so you map dimension 3. Okay, so you map, this is where you map 1, you map 2, you map 3. Okay, so you can look at other embeddings, okay, and essentially what you need is a gram matrix of all the points to be invertible. Okay, so this you can check that this will be enough. And so here, why is it interesting? Because phi of x transpose here. Okay, then if I take, so this is the element, the canonical basis. Okay, if I take EI times EI transpose, I will get a diagonal matrix. So I get diag of E of x. Okay, so I get like 0, 1, 0, and 0 everywhere. Okay, so this means that essentially when I'm in the one hot encoding, everything happens on the diagonal. Okay, so I end up with element of the diagonal. I map x to a 1 in the diagonal. So it's one hot encoding, but instead of being put in the vector, it's put in the diagonal. And the fact that the convex hull of those just a simplex is true. Okay, so it's a case where you can check that k is equal to k hat. Okay, why? Because if you take an element of V, so V is a set of diagonal matrices. If it is so it's that diagonal, it sums to 1, and if it is positive, the diagonal is positive. So I get an element of the simplex. So it's a hull of those points. Okay, so k is equal to k hat for discrete matrices.
Can you walk us a bit slowly? Like, what is the sigma? What is the u in the k?
So sigma, will be the integral of mu x, phi of x transpose. So it's a set of moments.
Mu of x would be what?
Mu of x, so here you want to check that, so k will be the set of integral of mu of x, phi of x transpose when mu is pointwise positive, okay, and summing to 1. It's the convex hull of all the phi transpose, this is k. And k hat will be something bigger, which will contain all of those, but you will replace mu being pointwise positive by this matrix being positive. Okay, so you just keep positivity, the action happens by replacing mu being pointwise positive by this matrix being positive.
I think, for this specific example.
Yeah.
So here is not the.
What?
I think for this.
For this, so this sigma is so phi of x transpose is diagonal.
Most what we are doing in this example. So since it is the simplest
Okay,
example,
okay.
and since I may be not the only one here,
Okay, sure.
try to ask.
No, good point. So here I take one x and I take this rank-on matrix. It happens to be a diagonal matrix.
That I got.
Okay. Now to construct K,
That is the definition.
so this is just phi of x. Now I want to define the set V, the hull of all of the span of all of that.
Yes.
So if I vary x, I'm going to put ones everywhere. I'm going to generate all diagonal matrices.
That I get.
So V diagonal matrices. Okay. Here U will be essentially identity over D or any. That will be identity because if I take the trace of identity, the trace of all of those is always equal to 1.
So what is the definition of U? What
U-
would I be thinking in this example to get into it?
So U is so that for all x, phi of x transpose U, phi of x is 1. It's just a representation of the constant function. So here, so U here will be U is U is identity. Okay. So now my set K hat will be the set of diagonal matrices of unit trace which are non-negative. So essentially, this is just functions, matrices which are diagonal with an element of the simplex in the diagonal. And the simplex happens to be the hull of the element of the canonical basis. And hence, here, K is equal to K hat. Because it's a very particular case where V is very small. Okay, so the hull is very small, so things are much simpler here.
So the basic fact you're using is that the diagonal matrix
This is
is PSP
the-
if and only
if
if all of the
elements are positive.
diagonal are non-negative.
Yeah.
Okay. So I didn't add anything because of that.
Okay, fine. Thanks. And so this is K equal to K hat view, but you could check that you can see the other view as well, but I won't do it. I will do it for the others.
So why did you call calligraphic V the hull? Maybe the hull?
V because it's vector space.
No, the hull.
Why? It's a span. The span. Sorry. I always get confused. Okay. So I always confuse lambda and gamma and span and hull. Sorry. So that's it's a linear span. It's span V for vector. And all right. So now let's take the other example. Quadratics. Okay. Quadratic function. Quadratic function on RD. Okay, let's take quadratic function on RD. So now I take h of x, essentially 1x transpose, okay, C B transpose BA times 1x. Okay, so x here is in RD. Okay, so phi of x corresponds to, well, 1x is in RD plus 1. Okay, and if I expand h like this, I get C plus 2b transpose x plus x transpose ax. Okay, so here it's a traditional way of presenting. When I say quadratic, I mean like constant plus linear plus quadratic. Okay, so constant plus linear plus quadratic. And I see it as a quadratic form in phi of x, where phi of x is this. Okay. Right, so the question is, when is H always non-negative? Okay, and is it H being negative? Is it always equivalent to H being a sum of squares? So let's have a look. All right, so let's take the inf over x in Rd of h of x. All right, so first, if A is not PSD, if A has a negative eigenvalue, the inf will go to infinity. Okay, so will be infinity if A not PSD. Okay, so I'm going to assume PSD. Now I can take the inf. So now I take the inf of a quadratic form. Okay, so the inf of a quadratic form, which is convex. So the inf will be C. I set the gradient to 0. So the gradient of h of x is 2b plus ax.
Minus infinity, right?
Thank you. So if this is 0, I get x is minus a minus 1 b over 2, and you trust me that at the end the value is minus, so now everything will fall back into place, okay? Happy now? Yeah. Always put a 1 over 2 for quadratic forms. It's a good thing to do. And you get 1/2. You get 1/2 of C minus B transpose A minus 1B at the end. And so this is the inf over H. So H is non-negative if A is PSD and this is positive. Okay, and so H non-negative come to A being PSD and C minus B transpose A minus 1B is positive. And this is the classical show complement version of positiveness of C, B transpose BA being positive. Okay. So this is PSD if A is PSD and the show complement of A is PSD, and this is a show complement. So what I've showed here is that H is non-negative if only if H is SOS. Okay. Here. So this is it's the simplest example where everything works out fine as well. I could have taken the moment view, so you can try that as well. So if I take the span of the convex hull of all the 1x times 1x transpose, you can characterize it as well, if you want. Lenka, you seem puzzled.
Yeah, okay. I'm not used to that. So what is the K and K hat here?
Here I have not. What would be K? K would be the convex hull of all 1x transpose. So this is the hull 1x x transpose x transpose. Okay? And you can check that the hull of that is all the PSD matrices with a 1 there. That would be the proof that K is equal to K hat. Okay, but here I took the SOS view, which is here a bit more direct. But the two are equivalent.
Can you just what is the SOS view and what is so I'm looking
SOS view is saying H is a quadratic form. I want to check, I replace non-negativity by being a sum of square. So meaning that the matrix representing my function is PSD. If I'm PSD here, H is non-negative, okay, and the sum of square relaxation is replacing this being, replacing non-negativity of the whole thing by PSD-ness of this. Okay, so this is the SOSU, and by convex duality, it is equivalent of being able to characterize the convex hull of this by keeping all the linear arguments. The affine arguments are kept. Okay, so the affine hull is kept, but you add PSDness of this. So the two views are exactly equivalent, and depending on the example, one is easier than the other. So here, SOS is almost direct, the SOS view. This one is also semi-direct, but yeah.
How can I modify this example in a minimal way to not get the if and not if?
Now it's going to appear in a minimal way. All right, so now we have done polynomials of degree 2 in RD. Let's do polynomials let's do polynomials.
This is also the convex hull is k is equal to k hat?
Yeah. So it has to be, because I've shown that non-negativity is like being SOS. Hence, it's equivalent to say k is equal to k hat.
So in the moment that, okay.
So polynomials in 1D of degree 2r in 1D. Okay, so this is phi of x being 1x x squared up to x power r. Okay. So here I will follow the SOS view. So the question is it true that if I have a polynomial which is non-negative, is it a sum of squares? So it is true. Okay, so proposition, and in fact, a proposition H a degree 2r polynomial. So an element that can be represented as a quadratic form in phi of x is PSD if only if H is SOS. And what is the proof? The proof is here very simple. Not very simple. This can be like, so my daughter is going through class préparatoire, so this is a good exercise for class préparatoire, this one. Okay. All right, so the proof. So the proof is simple. So since I have a polynomial, it has roots, which are either linear roots, real roots, or complex roots. So you can always write h of x as a product of the roots which are real of x minus real roots, okay, times the product of the complex conjugate root. Okay, when you have a complex conjugate root, you get something of the form x minus aj square plus bj square. Okay. So x minus aj square and now bj square. Okay. So this is like my generic way of writing a real-valued polynomial. Now I'm going to assume it's non-negative. Okay, so it is, of course, there is a small constant, okay, which I will assume to be. So now I have to, if I assume h is non-negative, okay, then clearly c has to be positive. Why? Because the limit at infinity has to be positive, so c has to be positive. Okay, so if h is non-negative, this is positive. Then if I have non-negative, this is non-negative, so this is taken care of always. So here this will change sign at every ri. So the only way to be non-negative is to have multiple roots, okay, and it has to be at least the order of multiplicity has to be even. Okay, otherwise, it has change sign at ri, and it cannot be non-negative. And that's it. Why? Because now I can expand that product. So I have like, I expand that product. So if I have like, let's say I have a cardinality of j product, so I can expand this as a sum of 2 to the cardinality of J element, okay? And each of the, I can expand the product, and each of the elements is a square, so I get the sum of squares. Okay? So this is a simple statement that if D is 1 and R is anything, well, R is even, of course, R has to be even, okay? So an odd polynomial, odd degree polynomial will never be positive, okay? Because it has to be positive and negative somewhere. So what I have now for polynomials, what I've shown is that I have equivalence if R is 2, D is 1, and if D is anything, and no, D is D. Yeah, start again. Yeah. So I did D is equal to 1, and R is positive, and I took D is positive, and R is equal to 2. Okay, this is the cases I've done. Question is, are there other cases where everything is tight? So this is a tight cases. Okay, so this was a question from Hilbert in 1888. 17th problem, I think. I checked the train. Okay, so that's why. And there is one more. Element for which there's one more case for which you have the thing is correct. Is D being 2 and R equals 4. So it is true that all the polynomials in two variables of degree 4, non-negativity is the SOS. Don't ask me why, it's true. And those are the only cases. Okay, so anything beyond that is not true anymore. So anything beyond that, so SOS polynomials are strictly included of the non-negative polynomial. Non-negative polynomials, okay. If you're not in those cases, okay, and there's one, I'll give you one counterexample, okay, and one example with D is 2, R is 6. I don't know it by heart, huh? It's 1. Minus, and I have no clue how to show it. Okay, so this is a.
This is R the degree or is 2R the degree? I'm a bit confused from the two.
What?
Is the degree R or 2R? I'm a bit confused from the two.
So this is R.
Degree R, which is even.
Yeah. So anyway, even has to. You have to be even, otherwise it's meaningless.
Yeah, so the statement is actually
No,
2
but
for
this is
0.
2R over there, right?
Yes.
2R equals 2, right? The 2R equals. Okay.
Sorry. So I am mixing. Okay.
And 2 are equal to 6.
So 2R is equal to 6, right?
Yeah. So equal to 6. Yeah. Yes. It's always the issue is that okay, because you have the product phi of x times phi of x, you double by and they get mixed up. So this is the one by Motzkin. This one happens to be non-negative and not a sum of squares. And how to show that? I didn't check. Can look. And this is Motzkin.
You plot it.
Yeah, you plot it, but it's 2D. Yeah, you can plot it. Proved by no, but for not being SOS, you have to solve the SDP. Okay, and it's Motzkin from 1965.
It's already not obvious that it's not negative.
Yeah, totally. Yeah, because you cannot put it as a sum of square to show non-negativity. So otherwise, that's gonna. All right. So this is one example.
If you do arithmetic geometry for the first 3 terms, I guess it is positive.
So do you have an argument to say it's positive?
Yeah, the average of the first 3 terms is bigger than their geometric mean. Oh.
Jolly, very good. Okay, so we have a proof non-negativity. Okay, that's very good. And SOS you can check by just solving the SDP. So that's this one, all right. So this means that for polynomials, okay, the hope of having a tight relaxation, which was like laid by the first 3 examples, is not true. So whenever we're going to do our Sos relaxation, it will not be tight. That's why this is where life gets complicated, because tightness is not ensured as soon as you go like D and R being like not simple numbers. Okay? So there are two ways about that. There is a classical way, which I will not do too much, and there is the other way that I will show you tomorrow. Let me just like give a highlight of the classical way. Yeah.
This example, does
Yeah.
it make sense like to think in terms of the dual approach, like to think what is there on top in k hat, or it's not really?
To me, like geometry dimension more than 2, 3. I'm willing to negotiate, but more than 3, it's difficult. I don't know. I didn't try, but there are probably illustrations showing why this is very special, but I wouldn't know. Totally not aware of that. That's,
And like in general, when is it, because so I see that sometimes it's useful to think direct and sometimes dual, and which
it's always equivalent. So sometimes you get more mileage out of one formulation. Sometimes you get more mileage out of the other formulation. It's always convex duality. It's always present, and sometimes. Let's take, for example, the last example, which be trigonometric polynomials. So this one is nice. So trigonometric polynomials. So let's take, and okay, so I went through the pain of having like Hermitian matrices, so let's do that example. So Trigo Polynomial. So we're going to do something like not standard. Let's put -1, 1 to the d. Okay, so I'm going to consider like periodic functions in -1, -1, 1, sorry. That will be 2 periodic. Okay, so this corresponds to take phi of x being the exponential of I pi omega x for omega in -r minus 1 up to r. Okay. So this is, you take all the frequencies between -r and r, okay, and you get like your trigonometric polynomial, and the set of functions which I include are all the functions for which the Fourier series has only non-zero coefficient for the first r frequencies. Okay. And now the question is, so when I take phi of x transpose h phi of x, so it is a trigonometric polynomial, and the question is, when is it non-negative? Okay, so there are two ways. I could play the same way as for polynomials. Okay, I factorize it and it's complicated. Or I can give it a name, and it's called the Phasor Ris Theorem. Okay. So this means that the proof is a bit too complicated. But what is this theorem? In fact, it's better viewed in the dual view. So what is k and k hat here? And I will. So what is k and k hat? So remember, what k is the hull of phi of x. So what is phi of x times phi of x complex conjugate? If I take the element omega, omega prime, I get exponential of I pi. So omega x, I get omega minus omega prime of x. Okay, this is if I take this for omega and the complex conjugate for omega prime, so I get minus omega prime, and I factorize and get this. Okay. So what is so this is a set of a matrix of size. So here there are 2r plus 1 element. So the matrix of size 2r plus 1. Okay. And the element omega omega prime depends only on the difference between omega and omega prime. So what I have a tuplets matrix. So it's tuplets. So this means that I will get like essentially this will be constant over all the diagonals. Okay. Okay. So here the span is a set of tuplets matrices.
So
Okay, so
These always have a common diagonalization, right? And so that should
No.
be a way, no?
aha! They're not circulant. No, the circulant ones are commonly diagonalized in the Fourier basis, but not the tuplets ones. Ah, I got you. Once. That's no, but in fact, but you're right. In principle, you're right. All tuplet matrices, if you let these grow, will end up being diagonalizable in the same basis when n goes to infinity. So you're right in the asymptotic limit.
Okay.
There's a very nice book by Robert Gray from Stanford only about that. But I do think as tuplets as being easily diagonalizable. Okay? And I will come back a lot, in fact, on Friday. So now what is k hat? So here k hat then I'm finished. So k hat. So what is k hat? This is the set of tuplets. So you have to be tuplets. Okay, you have to be unidiagonal. Because when omega is omega prime, you get 0, you get 1. Okay, so the way to think about it is that you take phi of x transpose, you preserve the affine hull, and you add PSD-ness. Okay, it's always the same thing. So the affine hull is tuplets with unidiagonal, and you add PSD. And this is k hat. Okay, so it's always the case that there's always the affine part, which is just like looking at the affine hull of your set of matrices, and you add PSD. Okay? Another question is, when is this something of the form integral of mu of x exponential of I pi omega minus omega prime of x? Okay, for mu probability measure. Well, this is k, and this is the Phasor Ris Theorem, saying that if you PSD and tuplets n in diagonal, okay, then there exists a measure which is like that. Okay, so the proof is not easy, but this is used quite often in signal processing. Okay. And the proof I won't give because I don't know it, in fact. I don't know it.
So this is an example where you don't have simultaneous diagonalization, so they don't commute, but it's still
exactly. So if I were to replace minus 1 1 by the grid, the regular grid, then that would be tuplets will be replaced by circular. They will all commonly diagonalizable, and that would be true. So these were all the nice cases where things were tight. And what I will do tomorrow, I will first go over what needs to be done to take care of situations where things are not tight. Okay? And what we will need to do is add extra constraints. Okay? This will be, and I forgot to mention references, and I will end with that. So important references, so refs. So here, when you do with SOS polynomials, you have two schools. You have the American school and the French school. Okay, so I'll start with the French school. And the French school, this is Lasserre. Okay, so Jean-Bernard Lasserre has a bunch of books, very good books of various years, where this is well explained. And Lasserre, of course, and colleagues. And other like source is Pablo Parillo. Okay. And they both like derived the basic principles like around the same time in the early 2000s, and those like are the starting point of all that. But I like the books by Lasserre because he has books where this is explained. And
it's also the Russian school.
Nesterov as well a bit.
Now Musho done something like along some basic version of it in the 80s.
Or you play the Russian trick done like earlier by the Russians, okay. Probably. Do you have a reference for that?
About
But if you have a reference for that, I'd be happy to have a look. I know Nesterov mentioned like the degree 4 things in one of his papers long ago, but I'll be happy. But this is the two sources. But Lasser has plenty of books, and so what is the program? The summary for today? I think this is yes. So the idea for today was to understand this duality between being sum of squares. So I get a function. Let me write some summary here. So I take h of x, which can be represented as a quadratic form. And the question is, okay, so we know that h SOS implies h non-negative, and h being SOS is not equivalent at capital H being PSD. Okay, it's PSD plus something, and that can make the function h equivalent to u. Okay, so an element of the orthogonal of V. And there is K, which is a convex hull of phi transpose. Okay, included in the affine hull intersection PSD cone. Okay, this is what we have done essentially. Okay, so the span is just linear span, and my U business is just to take care of the affine constraint. Okay, so this is like those statements are almost trivial statements. Okay, SOS is non-negative. The convex hull is inside the affine hull and it's PSD. Okay, and the question is, when is this equality? This is equivalent. If you equality there, you get equality there for all h. And this happens only in a few examples. Okay, so polynomials with good degrees. Okay, trigonometric polynomials. You have the quadratic functions, and you have quadratic functions on the sphere. That's pretty much it. Okay, for the exactness. Okay, so what we will see tomorrow, we will see what can be done when we have a strict equality. So you need to take some more inequalities, and that will be very easy for the trigonometric polynomials. You simply add more frequencies. You embed your set of frequencies in a bigger set of frequencies. That's somewhat natural. For polynomials, it's going to be like more complicated. Okay, so I won't do it. I will just mention it. Yeah?
For the trigonometric polynomials, but what will be different? Because here we show
in higher dimensions. In higher dimensions. Okay. I will go over the Boolean hypercube also, because I think Boaz will be much more knowledgeable than I do here. And for all of those, I will need to add extra constraints. So it will be the classical SOS view, essentially like Lasser and Parillo and all the people that have worked on it later on. And then I will move on to our own work, where we get rid of all those hierarchies by letting phi of x being infinite dimensional. Okay? And by doing this, we're going to get rid of, we always get this being equal, okay? But now phi is infinite dimensional, so we have to deal with it, okay? And that will be the topic of the, how you deal with it in a tractable way. So you're going to, yes, kernels RKHS. Phi, spoiler, is going to be the feature vector of an RKHS. And everything will go fine. This will be for next lecture, and the last one will be on looking at beyond optimization. Okay, so here we minimize functions, but sometimes you want to compute like log sum exp. Okay, probably also in physics. The name is free energy. Oh yes, free energy. And it turns out that you can also compute free energy with sum of squares in a way which I will describe at the end of the lecture. Thank you for your attention, and questions.